Let's look again at the titration of a weak acid and a strong base as it relates to what's happening in the beaker at each point during the titration. Okay, so in the beaker at the beginning of the reaction, we have, this is my beaker here, we have 0.010 moles of HAC, which I'm going to represent by 10 H pluses and AC minuses. And initially, that's the only thing in my beaker. So initially, when I want to find the pH of the solution, we have that H3O plus times AC minus over HAC. And so all of this will be on my HAC, and then this will be X and X, so I'll end up with X squared over whatever this ended up being divided by its liters, so it's molarity. And that'll be my H3O plus, and that'll be how I'm going to find my pH. Oops, let's get rid of that. There it goes. But what happens if I want to add some base to it? So, there is some base. So let's take that base and put it in my container. Now the base initially is together until I put it in my container, and as soon as I put it in my container, the OH and the Na separate from each other. And the NAs become spectator ions, and they're just floating around, la la la, floating around. And the OH minuses, on the other hand, they attack this HAC. So the OH minus will attach itself to the H plus to make some water, and we'll have some AC minuses floating around. This one's going to do the same thing. It'll attack the HAC to make some water, and the AC minus. So the NAs are spectatoring around, and the waters are in excess, and they're just spectatoring around, and so we have AC minus. So when you're finding your Ka, again, same equation as we had before, H3O plus times AC minus over HAC. Your concentration of HAC has gotten just a little bit less for the bottom, but your concentration of AC minus has gotten just a little bit more for the top, and your H3O is still your X. So now you're in buffer zone, where you have the acid and its conjugate base, because we have added some OH minus, so we have produced some conjugate base. Let's get rid of that writing, and let's add a little bit more base. Not a lot of more base, but just a little bit more base. Let's say enough base to get us to the midpoint of the titration. So I have some NaOHs coming in. The NaOHs are going to hang out. Let's move it back over and zoom in a little bit. Okay, so remember what happens. As soon as those NaOHs get in, they separate. See if I can get it to separate, and the Na starts floating around as a spectator, and the OH minus attacks the HAC to make some water, and the AC minus is floating around, so the NaOH is going to attack the HAC, so that we have AC minus floating around, and H is going to go with the OH to make some water, and the Na kind of floats. And let's do it again over here. Let's see if we can get the AC minus to float, the NaOH to float. So we end up with water and Na, spectator, spectator. So I'm just going to make everything kind of on one side. Even though the NAs are floating wherever they want to, I'm going to move them all to the left and all the waters to the right so they kind of get out of my way. But they're just everywhere. So now look at what we have. We've got the same number of AC minuses as we have HAC. We are at the midpoint of the titration. So when you do Ka is equal to H3O plus times AC minus over HAC, we have the same number of HACs as we have AC minus. This happens at the midpoint. So these numbers are going to cancel out, and we end up with Ka is equal to H3O plus, or pKa is equal to pH. This happens at the midpoint of the titration because I've gotten rid of enough HAC to produce the same amount of AC minus as I have HAC. Alright, well let's add a little bit more base to this solution. Ooh, look, there's some base. Ooh, look at all that base. And I'm going to get rid of those Na spectators, but remember, they're still down there. I just don't really care about them because they're spectators. So let's add that NaOH. The NaOH is going to attack the HAC. Attack, attack, attack. Well, the first thing that's going to happen is the Na is going to go off. The Na is just a spectator anyway. The Na doesn't really care. You guys can do whatever you want. He's just going off. And the OH minus is now going to say hey to the H plus and make some water. And let's move everything together. All of these things, remember, are just floating around freely. So I don't have to have the waters all in one place. You can put them anywhere. But I'm going to put them all in one place to make them kind of easier to see. But just remember, everything's just floating, free-floating spectator ions. And check it out. I have 3 really nice categories. A bunch of excess water, a bunch of spectator Na pluses, and then some AC minuses. So now, when we're at the end point, the only thing left in my beaker is AC minus. AC minus is it. So when I'm writing the Ka expression, that's H3O plus times AC minus over HAC, this won't work because then I'm going to have to put a 0 in for HAC. You cannot divide by 0. This is not the Ka expression for HAC because there is no HAC. Instead, this should be the Kb expression for AC minus. That is AC minus plus water is going to make some HAC plus OH minus. So that's HAC times OH minus over AC minus. And now your AC minus is going to have this huge number, and these guys are both going to be initially 0, so at equilibrium they'll be x, and so you'll do x squared over the concentration, but for Kb, not for Ka. Okay, but what happens if you're going to add in some more NaOH even after you've reached the equivalence point? Oh, look at that. There's some more of that just hanging out over there. So let's add some more NaOH. And I'm going to zoom in here. So when you add some more NaOH, the first thing that happens is the NAs say, see you later, we're going to spectate from down here. These are the bleachers. And so now we have OH minus and AC minus. So the AC minus is going to react with the water to produce HAC and OH minus. But remember the percent ionization. For HAC is like 1.9%, but for the AC minus it's even less than that. It's something like less than 0.01% ionized. So the AC minus is going to produce relatively none OH minus. On the other hand, you have full OH minuses right here. So when you're looking for the pH, all you care about are these guys, the OH minuses that are real OH minuses, not the less than 0.01% of the AC minuses that are actually going to turn into OH minus. So this I don't care about, this I don't care about, this I don't care about. When I'm finding the pH, I only need the negative log of this, the OH minus. And that's our titration of a weak acid and a strong base. I hope it was a little bit more clear. I also hope you didn't think I was going to leave it like that. POH is equal to the negative log of OH minus. pH is 14 minus that. Okay, that's our weak and strong titration. Join me next time for whatever it is that comes next.